Okay, so we were working with vectors, and on Friday we looked at these two vectors, a 40 Newton force acting at 30 degrees and a 20 Newton force acting at 60 degrees, and our question was, what one single force can do the same job as those two acting simultaneously? And the first thing we did was we put these two vectors in head-to-tail form and we solved graphically. So if you redraw them in head-to-tail form and then you draw a resultant from the starting point, let me try that again. A little bit better. I'll call that vector R for the resultant. And we use the law of cosines and the law of sines to get the answer. And does anyone recall what that was? Manav?
The resultant was 58.2 newtons.
At what angle?
39.9 degrees.
Then we went and we solved it a more sophisticated way using the component method. So we drew each vector independently and we broke each vector down into parts. And this 40 newtons could be broken down into a horizontal part and a vertical part. Those parts called components. And using SOHCAHTOA, what did we get for the horizontal component of that? David?
34.6.
And what about the vertical component, David?
And 20.
And we broke that 20 newton up into components. How much? And then we took the sum of all the forces in the x direction and got the total resultant of those. And then we took the sum of all the forces in the y direction and got the sum of those components. And then we found the resultant of those little mini resultants. So the sum of all the forces in the x direction would be 34.6 newtons plus 10 newtons, and that turns out to equal 44.6 newtons. And then the sum of the forces in the y direction would be 20 newtons plus 17.3. And then that would be 37.3 newtons. And then if we draw a head-to-tail diagram of these sums, we can get our answer. So if I draw, what was the magnitude of all of them in the horizontal manner?
44.6 newtons.
44.6 newtons. And Manav, what about that vertical?
37.3.
37.3 newtons. And then using Pythag and SOHCAHTOA, we got the resultant vector R again. And it was 58.2 newtons
At 39.9 degrees.
at 39.9 degrees. All right. Does that refresh everyone's memory? Yes?
Sir.
So this component method, where we take the original vectors and we break them down into parts like that, this could be shown with a more sophisticated notation. And this sophisticated notation includes using unit vectors. Now a unit vector has a magnitude of 1, and it doesn't have any units. Its only job is to indicate direction. So for example, if this first vector over here, this 40 Newton at 30 degrees, if I call it vector A, that little half arrow, that's the lazy man's way of drawing the vector symbol, a full arrow. I could rewrite A in terms of its components and unit vectors. Vector A could be rewritten, vector A is equal to the component of A in the x direction that's just a number. That's a scalar quantity. Magnitude, just a number in units, A sub x. But I want to give it direction now. So instead of saying horizontally to the right, I could just say multiplied by a little baby vector that's pointed to the right. Unit vector I. Now, this is a vector. I could put a vector symbol above it like that, but it's a special vector. It's a unit vector. It only has the magnitude of 1. So to indicate that it's a unit vector, we don't use the regular vector symbol. We use a hat. It's like this little symbol here. Whoa, what happened there? Plus the component of A in the y direction, that 20 newtons. But it's the vertical component of A, so it's frequently called A sub y. But we want to indicate the direction, so instead of saying upward or in the positive y direction, we just multiply it by a little baby unit vector who always points in the y direction times unit vector j. So a more sophisticated way of writing vector A would be to say it's equal to A sub x times unit vector I plus A sub y times unit vector j. Or if I want to put in the values, I could say vector A is equal to 34.6 newtons times unit vector I plus 20 newtons times unit vector j. Likewise, I could draw vector B. I could state vector B in terms of its unit vectors. Vector B over here, the 20 Newton one, I'm going to call that vector B. Vector B would be equal to the component of B in the x direction times unit vector I plus the component of B in the y direction times the unit vector j. Or if I want to write it in terms of the actual number values, in this particular example, vector B would equal 10 newtons times unit vector I plus 17.3 newtons times unit vector j. Now notice, if we go back to that original head to tail diagram, our vector R, the total resultant, goes from the starting point and headbutts the last vector added, right there. if I drew the vector components of R has the x component that goes from here out to there. That's the component of the resultant in the x direction. And then it has a component in the y direction. That's R in the y direction. See if you can follow me on this, people. Watch. Instead of saying vector R is 58.2 newtons at 39.9 degrees, a more sophisticated way of saying vector R is I could say vector R is equal to its x component times unit vector I. That tells you, oh, to the right in the horizontal direction, plus the component of vector R in the y direction times unit vector j. But look, what is R sub x equal to? Take a look at these baby vectors over here. You know, here when I found for vector A, if I broke it down into parts, look, here's the horizontal part, from there to there, A sub x. And then for vector B, here's the horizontal part for vector B. And we did this with the component method. When we wanted to find the whole shebang, sum of the forces in the x direction, what did we do with the component of A in the x direction and the component of B in the x direction? We just added them. So it turns out that R sub x is just A sub x plus B sub x. Times unit vector I. Likewise, R sub y, this whole shebang height over here, it's just the sum of the two y components, A sub y, plus B sub y. And you can see, look, if you add this length here and that length there, you get the total length right here. Like that. So, the resultant, R sub x times unit vector I plus R sub y times unit vector A, could be rewritten as vector R equals AX plus BX, adding the horizontal components, times unit vector unit vector I plus AY plus BY times unit vector J. And that's exactly what we did with the component method. If we scroll ahead, we broke each vector down into its components. And then we put those components in head to tail form. Well, what is this horizontal component right here? It's AX plus BX. What is this vertical component right here? It's AY plus BY. So, from now on, if if we want to describe a vector, if we want to state a vector, we could do it one of two ways. We could say, hey, the resultant is 58.2 newtons at 39.9 degrees. Did I get those values right? Yes?
Yeah.
Or we could state that same answer in terms of unit vectors. Vector R is equal to, what was the total amount in the x direction? 44.6 newtons times unit vector I plus 37.3 newtons times unit vector J. Both of those give us everything we need to know about vector R. It's two forms of the same answer. Sometimes that top answer is known as stating the answer using polar coordinates. R and theta. Polar coordinates R and theta. R is the magnitude of the vector. Theta is the direction given by the at angle. Or you could describe a vector using rectangular coordinates, also known as Cartesian coordinates. Where x is the component of the vector in the x direction, and y is the component of the vector in the y direction. Anyone want to take a guess why they're also called Cartesian coordinates? Brett?
They were written out that way by Rene Descartes.
Yes. And Rene Descartes was also known as Cartesium. Pretty sure, yes. And he was a French mathematician, philosopher, physicist in the 16th century. And he's also widely known for a very, very popular quote. Do you know Brett?
I think therefore I am.
Yes. Yes. It's the same guy who came up with that quote, I think, therefore I am, came up with the rectangular coordinate system of plotting things out. And ultimately, his work laid the groundwork for calculus. Question, comment? Yes?
Any ready for this?
Of course. Now, you want to get very comfortable converting between these units. So, if we have a vector A and we want to know its magnitude. The double absolute value sign, the double lines like that, that means the magnitude of that vector. Now remember, if this is vector A, vector A can be rewritten in terms of its unit vectors. It's A sub x times unit vector I, and this is A sub y times unit vector j. So if you wanted to know the magnitude of vector A in terms of its components?
The square root of ax squared plus ay squared.
Exactly. If you wanted to know the at angle given AX and AY, that at angle right here,
One question: why are we squaring this for A, not for R?
we're just looking at one vector right now, vector A. So this would also apply to vector B, and this would also apply to vector R. So I could also say vector B, went up like this, yes? Vector B could be rewritten in terms of its components. So vector B could be rewritten as bx times unit vector I, by times unit vector j. Those are the components of B. And if I wanted to write, hey, what's the magnitude of B? Well, if you knew the two legs of the right triangle and you want to find the hypotenuse, you can use the Pythagorean theorem. So what would the magnitude of that vector B be if you knew what bx and by were?
So is this just doing it without the vector and not just? I don't know why you can do this with R.
We can also do this for vector R for the resultant. If I have the resultant vector,
Is this the Cartesian way?
we're talking about how to convert between Cartesian and polar.
Okay.
How to go back and forth between them. So let's say you had vector R and you were told the component in the x direction times unit vector I, and you were told the component in the y direction times unit vector j. So maybe I should make this a little clearer. Given Rx and Ry, find the magnitude of R and the value of theta. So how would you find the magnitude of R if you knew the components? Pythagorean theorem. The magnitude of R would equal Rx squared plus Ry squared. And how would you find the at angle if you knew Rx and Ry?
Like tangent of y over Rx.
inverse tangent. Because tangent of theta so this is true for any vector, whether it's vector A, vector B, or the resultant, vector R. If you want to find the magnitude, you can take the square root of the components. The square root of the sum of the components squared.
Yeah.
And if you want to find the direction of any vector, it's inverse tangent of Ry over Rx. Now, on the other hand, what if you're given the magnitude and the direction and you want the components? So, back to, what if you're given the polar coordinates and you want the Cartesian coordinates? So it would be something like this.
So this is from Cartesian to polar,
Yes.
and the other way was the other way around.
Yes. So this time, given the magnitude of A and theta, find A sub x and A sub y. What would A sub x be equal to?
R cos theta. I mean, like theta.
In this case, it's going to be the magnitude of A
over R, yeah. And then cosine of theta.
times cosine of theta. Using, the cosine of theta equals adjacent over hypotenuse. Cosine of theta would equal AX over the magnitude of A. And likewise, what would AY equal? Well, the magnitude of vector A times the sine of theta. And of course, that would be true for vector B, and that would be true for the resultant vector, vector R. So, in summary, if you have vector A and you know its components, AX times unit vector I plus AY times unit vector J, and then you have vector B and you know its components, BX times, unit vector I plus by times unit vector j. If you want to find the vector sum, also known as the resultant, you could easily state what the resultant is in terms of the unit vectors. And what would go in that parentheses in front of the I, Sam?
AX plus BX for the first one,
Yep,
and then for the second one it's AY plus BY.
exactly.